I didn't hear you come in. You just caught us as we were starting our evening dinner, but I'm happy to see you, and by now you've finished calculus for a little while, and we're going to move on to vectors again. So the vectors unit is going to be very different than what we studied before in vectors, but it's definitely going to switch gears from calculus. So it's going to be very important that you're keeping up in this unit because it really builds upon each other. We're going to look at lines, equations of lines in 2 space and in 3 space. We're going to look at equations of planes as well. But don't get too nervous, it's not rocket science. Actually, I guess it kind of is rocket science technically. Don't worry, that's not the last time I'll tell that joke. It's such a good one. Alright, so dinner can wait. Come on, let's get to it.
So finding the equation of a line is something you're familiar with all the way back from grade 9. We're going to look at 2 different types of equations today called vector and parametric equations. So you're most familiar with equations of lines in the form y equals mx plus b, or sometimes called slope y-intercept form. Given 2 points on a xy Cartesian plane, you can find their slope and then use that to find the equation. Now think about it this way. Think about the equation of a line. The slope is kind of being like the direction of the line, and a point being the position of the line. In fact, that's exactly what lines in the Cartesian plane have. They have direction and they have position. They're different than vectors. Remember that vectors don't have position. Vectors have magnitude, so they have a length, and they have a direction, but they don't have a position the same way that a line does. We're going to take this idea of finding the equation of a line, and we're actually going to show how we can use vectors to come up with the equation of a line. We're going to start in 2 space, and it's going to be a little confusing because it is different than something you've learned before, but then we're going to take that, we're going to be able to use that to talk about lines in 3 space or in 3 dimensions as well. Now sometimes the notation R2 is used for 2 space. So what we're going to do is we're going to talk about a point on the line and a vector that has the same direction as the line, or what's called a direction vector. So take a look at this example where I've got some numbers here. So suppose I want an equation of this blue line. It goes through the point 4, 3. And you can actually count the slope here. If you look at the rise and the run between these points right here, you can see that the line has a slope of -1/7. So of course I can use the slope and this point to come up with the equation, but that's not what we're trying to do here. Notice that if the slope is -1/7, this vector, which has been called vector m, actually has the same direction as the blue line. So one way that we could use vectors to talk about this blue line is we could say start at the point 4, 3 and then add any combination you want or any amount of this vector m. So one way of getting points on the blue line, take the point 4, 3 and add the vector m, -7, 1. If you were to do that, you would get, let's see, in this case, you would get -3, 4. So if I add 1m, sure enough, I get to the point -3, 4, which is right there. Now I can add, instead of adding -7, 1, I could add half of -7, 1, and then I would get to whatever this point is right about here. I could add a third, and I would end up somewhere here. I could add 2 of these red vectors, 2 m's, and I would end up somewhere over here. I could even subtract m's and end up over here. So what we say is this is actually, I'm going to put t here, where t is any real number. We call that a parameter. We can actually say that this is an equation for the blue line. An xy point is given by taking 4, 3 and adding any amount or any scalar multiple of the vector -7, 1. And that's called the vector equation of this line. And I've shown how for t equals 1, you'd get to the point -3, 4. Now technically, the point xy is technically a vector because you're using vector math here, but it's a vector that represents a point on the graph. More general, we can talk about it like this. So imagine you have a line and you want to find its vector equation. So one thing you could do, that line might have a point, what we call an initial point, x naught, y naught. So remember that x naught, y naught is often used for like initial. So in this case, an initial point. I'm just going to sketch it right there. And then if the line has some direction vector AB, perhaps it goes that way, but it could go the other way. Then one way to describe points on the line is to say that every point on the line can be arrived at by taking your initial point and adding any amount of the direction vector that you like. So one way to get to a point in the line, start at x naught, y naught, and then add 3 direction vectors. 1, 2, 3. Now you're down here. It looks like you're close to the y-intercept. Or you could subtract a direction vector. Start at x naught, y naught, subtract a direction vector, and go the opposite way. End up with a point right here. Or you could subtract 10 direction vectors. You could add 20 direction vectors. You could subtract a half of a direction vector, get you somewhere right there. This is called the vector equation of the line. Now, you'll often see xy equals. You'll sometimes also see it written like this with an r. That's common as well. And in this case, r just means the position vector of some point on the line. Let's take a look at this example. Find the vector equation of a line passing through 2 points. And then find the coordinates of 2 other points on the line. Now, I realize that it would be easy to use y equals mx plus b form, but we want to come up with vector equations in this case. So we need an initial point and a direction vector. Well, the initial point's easy. There's 2 of them. We can use whichever one we want. The direction vector, well, our line is going to have the same direction as vector PQ. We haven't done this in a while, but remember to find the vector from P to Q. You go 5, take away 1, which gives you 4, and 5 take away -1. I've said that wrong, pardon me. You subtract components to get the vector that goes from P to Q. So the first one will be 5 subtract -1. And the second component will be 5 subtract 1. So that PQ, the vector joining P to Q, is 6, 4. Okay, now if we think about our line through the points PQ, we need a direction vector. We need some vector that has the same direction as line PQ. Well, the vector PQ works, 6, 4, so that's fine. We can use that, but actually there are other vectors that work as well. Any vector that has that direction would also work as a direction vector. So it could be shorter than PQ, it could be longer than PQ, it could go the opposite direction as PQ. One really simple idea here is why use 6, 4? Because a simpler vector that would have the same direction would be 3, 2. Notice how I just divided both of those by 2. Why not make that direction vector small? Why not use smaller numbers? Technically, -3, -2 would work as well, because that would just be a direction vector that goes in the opposite direction as PQ, which is fine, because it doesn't matter which way our direction vector goes. So the direction vectors are not unique. Once we get that, we now have our equation. I'll choose the first point as my initial point, -1, 1, plus any multiple of my direction vector. So where t is any real number. I don't have to use t for my parameter, it's just very common. S is also very common to use for parameters. Notice the vector equation of a line is not unique. It would not be wrong to replace -1, 1 with 5, 5, and it would not be wrong to use 6, 4 instead of 3, 2. It'd just be odd. And it wouldn't be wrong to use -3, -2. It would just be, again, it'd be just strange to do it that way. So notice this little sentence here. Every value t specifies, that should say 1 point on the line. So every time you use a different value of t, you will get a different point on the line, and the other way around is true as well. Once you're given a point on the line, there's only one value of t that corresponds to that point. Now keep in mind, t doesn't have to be an integer. It could be a half or a third or anything like that, 2/3 and so on. So some points on this line here, if I were to sub in, say, t equals, well, let's use t equals 1, then I would find that 1 point on the line is equal to -1, 1 plus 1 times 3, 2, which would give me the point 2, 3. So there's a point on the line, 2, 3. If you sub in t equals 2. I actually believe you end up getting the 0.55. You could sub in t equals 3 to find another point, or t equals -3. T equals 0, of course, will give you the point -1, 1. Okay, let's take this formula and let's actually rearrange it. Notice that my x value of 2, I got that from taking -1 plus 3t. So really, x will always be equal to -1 plus 3t when you choose your parameter, and y will be equal to 1 plus 2t. Those are actually called parametric equations. They're very similar to the vector equation, just with the x and y sort of broken up into two equations. Notice how different these are than finding an equation in y equals mx plus b form. When you have an equation in y equals mx plus b form, maybe it's like y equals 3x minus 5, you tend to sub values of x in and then find the corresponding y value. Whereas with parametric equations, you start by just picking a random t value, and that basically gives you your x and then your y value. In general, if you had a line with an initial point of x naught, y naught, and a direction vector equal to a comma b, then your parametric equation will be x equals x naught plus ta, and y equals y naught plus tb. Find the x and y intercepts of the line given by the vector equation, and there it is right there. Well, let's look at parametric equations. Are often a little easier to think of. Our x value is going to be 3 plus t, and our y value will be equal to 2 subtract 2t. Okay, if we want an x-intercept, at an x-intercept, y is always equal to 0. So sub y equals 0 into the parametric equation, and you get 0 equals 2 minus 2t, or 2t equals 2, t equals 1. So basically what this says is, look, the t equals 1 is the parameter that makes y equal to 0. Well, what does it make x equal to? 3 plus 1, which is 4. So there is the x-intercept at 4, 0. If you want to find, of course, the y-intercept, you can do that. The y-intercept is when x equals 0. So when does 0 equal 3 plus t? Using that equation right there, that happens when t equals -3. Well, if t is equal to -3, then y would be equal to 2, subtract 2 times -3, which is y equals, let's see, 2 plus 6, y equals 8. So we have a y-intercept at 0, 8. And now we move on to the real point of talking about vector and parametric equations, and that's so that we can talk about lines in 3 space. There is no such thing as finding the equation of a line in 3 space using y equals mx plus b. I mean, how do you even talk about slope when you're talking about 3 dimensions? Well, you can kind of talk about slope in 3 dimensions if you talk about a direction vector that has the same direction as your line. The only thing we need to do in this example, we can use everything we did before. We just need a third coordinate axis, and of course we use z. We've seen that little picture there, x, y, z. Generally think of x as kind of coming out of the page, y going to the right or the left, and z going up or down. So our vector equation is very similar. We just, of course, now have a z naught, and we have a third direction. It's often called a direction number. So our direction vector is now a 3-dimensional vector, a vector in R3. And of course, so is our point. Well, if we can do vector equations in 3D, we can do parametric equations in 3D as well. We just have 3 parametric equations, and there they are. All right, so suppose we have 2 points in 3 space, points A and B, and we want to know vector parametric, and this says symmetric, but you know what? We're going to talk about those during the next lesson. So if you see anything about symmetric equations in the textbook right now, we're going to deal with those in the next lesson. Okay, so the point A and B, so let's find, I mean, it's easy to find a vector equation. You need an initial point and a direction vector. Well, the initial point's easy, just either use A or B. Let's take a look at vector AB and see if it's a good direction vector. So 9 subtract 1 gives me 8, and 1 subtract -3 is 4. And 5 minus 5 is 0. So AB is 8, 4, 0. Okay, I could use that as a direction vector, but why not make it simpler and make those numbers smaller? Because guess what? Divide by 4, 2, 1, 0 has the exact same direction as AB. So that's a good direction vector. And our vector equation is going to be, okay, I'll pick point A, 1, negative 3, 5, plus t times 2, 1, 0. Solving for our parametric equations, the first one, x equals 1 plus 2t. Sometimes you'll see parametric equations just separated by a comma. Y equals negative 3 plus t, and z equals 5. Notice the direction vector for z is equal to 0, meaning z will always be equal to 5 in this example. Maybe it wasn't the most exciting equation of line in 3 space, because since z is 5, it's kind of like a line that just hovers above the xy plane. If you imagine that z's always being 5. You've got some line that just it's actually parallel to the xy plane. Don't worry, there's more exciting lines coming up. Also notice you don't need to write plus 0t. There's another way of realizing why that's just z equals 5. We can find another point on the line by just choosing a value for t. Let's use t equals, so we use t equals 2. If t equals 2, then x equals 1 plus 2 times 2, which is 5. Y equals negative 3 plus 2, y equals negative 1. And of course, z is always 5, and so another point on the line is 5 and negative 1, 5. In this next example, I'm asking you to find the equation of a line perpendicular to the xy plane and going through the point 5, 4, negative 5. Notice how those two clues, one gives me position, the other gives me direction. The first one gives me direction. It's perpendicular to the xy plane. Well, the xy plane is this area here, if you imagine shading all this area in right here. Okay, if we're perpendicular to that, it means the line goes straight up and down like this. And it goes through the point 5, 4, negative 5. If it goes straight up and down, I need a direction vector for it. Well, guess what vector has the same direction? 0, 0, 1. Yes, that vector lies along the z-axis. In fact, we often call that vector the unit vector k. Yeah, and you might say, well, that's not on the line. No, of course it's not on the line. It's a vector. The vectors always have their tails at the origin, so it's not on the line. It has the same direction as the line, or it's parallel to the line, if you want to think of it that way. So if you were to start at 5, 4, negative 5, and add that direction vector, you would still be on this line. So our vector equation is going to be 5, 4, negative 5 plus t times 0, 0, 1. And of course, parametric equations, x equals 5, y equals 4, and z equals negative 5 plus t. In fact, think about it. X is always 5, y is always equal to 4, and z is, well, really whatever you want it to be. Take negative 5 and add t, you'll get to every single possible z there is. It's kind of like a vertical line almost, or a horizontal line. It's almost like a special case in this example. Do the equations below represent the same line? Boy, one would hope that when we look at two equations, we could certainly tell whether they represent the same line or not. As it turns out, with vector and parametric equations, that's not always the case. It's not always that easy. If I look at this second line, let's write the parametric equations. Negative 1 minus 4t, 11 plus 10t, and negative 4 minus 6t. Okay, well, one way to talk about them being the same line is, do they have the same direction vector? Let's look at d1, the direction vector of the first line. It's 2, negative 5, 3. Notice I'm just using those values right there. Okay? The second direction vector, I can actually just use negative 4, negative 10, negative 6. Okay, they're not the same numbers, but notice that d1 and d2 are almost the same. In fact, if you take d1 and if you take, that's backwards. They are scalar multiples of each other, which means they're collinear or they're parallel. If you take d1 and multiply it by negative 2, you do get d2. So they're parallel lines, that's for sure. But that doesn't mean that they're the same line. Two lines can be parallel and not share any of the same points. That's true in 3 space and in 2 space. So they either share a point or they share all points. So how do I determine whether or not they share a point? Well, one thing I could do is I could look and I could say, okay, well, I know the first line has the point. Actually, let's go with the second line. I know the second line has the point -1, 11, -4. Is that point on line 1? Let's start by assuming that it is. Well, if it is, then that means x equals 5 plus 2s. It means -1 equals 5 plus 2s. Or -6 equals 2s, and that s is equal to -3. So if this point belongs to line 1, then it must be that s is equal to -3. Okay, well, if s is equal to -3, let's solve for y. Y is -4, subtract 5s, and s is -3, so we get y equals -4, subtract 5 times -3. Well, what is that equal to? Let's just see, that's -4 plus 15, which is 11. Well, that's good. How about z? Z is -1 plus 3s. And we've said that s must be -3. So -1 plus 3 times 3, z is equal to, 8. So no. The answer is no. Reason being, -1, 11, 8 is a point on line 1. Because basically in this step right here, we realize, look, if x equals -1, that only happens when s equals -3. And if s is equal to -3, then the y value is 11 and the z value is 8, not -4. So they are not the same line. They're parallel, but they're not the same. There it is. Parametric and vector equations. There's some questions for you to try. Not a whole lot of questions, just a few. They're on our course webpage. They're also right here from the online textbook. Okay, the one I told you how to access on mynelson.com in the previous email. Just shoot me an email if you have any questions or if you're having trouble getting to the textbook. Okay, bye for now.